You know the feeling when you want to take a picture and instead of grabbing the big camera, you just use your cell phone. It's smaller, it's faster, and surprisingly delivers almost the same results. It's very similar with low voltage transmission electron microscopes. In many cases, they can replace the big conventional TEMs while being more compact, more accessible, and quite often just as effective, or maybe even more. We will see. Good afternoon, ladies and gentlemen. My name is Jaromír Bačovský, and I work as an application manager in Delong Instruments, the developer and producer of this kind of unique low voltage transmission electron microscope. Welcome to this presentation. The story of low voltage transmission electron microscopes is closely connected to one very smart man, Professor Armin Delong. Professor Delong had a vision about compact and user-friendly transmission electron microscope, which would be available to all scientists for their routine work. So after a few years of development, he turned this vision into the reality. And he introduced the concept of a benchtop transmission electron microscope operating at very low energy, 5 keV, with very unique properties. And we try to follow this vision and develop this concept to the needs of modern world. But the portfolio of our company is much broader. It's like a tripod. The first pillar is custom solution, different project in electron optics and vacuum technology. The second leg of our tripod is the guns, Schottky field emission guns, especially appreciated in the semiconductor industry or by those who want to build their own electron microscope. And finally, our flagships, LVMs, low voltage transmission electron microscopes. In the beginning, let me introduce you two members of the LVM's Delong family, the LVM5 and the LVM25E. First, we have the LVM5, the smallest and currently the only true benchtop TEM on the market. And then its younger brother, the LVM25E, which delivers outstanding performance while keeping a compact and robust design. Both instruments follow the same low voltage philosophy, but each one is designed for a different level of performance and versatility, and of course, different applications. The LVM5 is our truly compact benchtop system. Despite its small footprint, it offers multiple imaging modes, TEM, SEM, scanning transmission, and electron diffraction, all integrated into one very accessible instrument, and its main application area are nanomaterials, basic characteristics of nanoparticles, or, for example, graphene. The LVM25E is the more advanced system. It provides high resolution, more imaging modes, and also some analytical capabilities, such as EDS for comprehensive sample analysis, while still keeping the design compact and easy to install compared to the conventional TEMs. Our low voltage transmission electron microscopes operate at accelerating energies between 5 and 25 kiloelectron volts. And because of this low energy approach, they offer several unique features and innovative technical solutions that conventional high voltage TEM simply don't provide. On this slide, you can already see a brief summary of these unique aspects of our technology. But before we jump into the details, there's one important question which should be answered first. Why should you prefer low voltage TEM instead of a conventional TEM operating at, 80, 100, or even 200 kiloelectron volts? The answer is very simple. To evaluate the image quality in electron microscopy, there are always two parameters which needs to be considered. The resolution, of course, that's where conventional big TEM excel, without any doubt. However, the second one, no less important, is image contrast, which is really significant feature of low voltage transmission electron microscopes. This lack of contrast is a well-known phenomenon in transmission electron microscopy, but our low voltage system can deliver this excellent contrast even for the sample made of light elements. typically biological sections or other carbon-based materials like graphene. And the explanation comes directly from physics. Slow electrons are scattered much more strongly than fast ones. While high-energy electrons pass through the sample almost unnoticed, low-energy, slow electrons have much more time to collect more information on their way through the sample. A direct consequence of this property is that we can reduce or even completely eliminate staining. And even without staining, we can still achieve results comparable to those from conventional TEMs with fully stained samples. And we all know that staining agents are not exactly pleasant chemicals to work with. Uranyl acetate, osmium tetroxide, extremely toxic, heavily regulated, and harder to obtain because of all the paperwork. So being able to reduce their use or avoid them altogether is a pretty big advantage. I can prove this contrast on a sample of cyanobacteria, which you can see. We imaged an unstained sample using a conventional TEM, and then the same sample using the LVM25E. And I think you can see the result speaks for themselves. You have already heard about the small footprint of our devices. This is important for many reasons, not only because the instruments take up very little space, but also because you don't need any construction work. LVM systems are designed to fit through a standard dorm frame, so installation is simple and fast. This level of miniaturization is possible mainly thanks to the smart and unique concept of electron optics. While conventional TEMs rely on electromagnets, large cores that needs many windings and thick wires to generate strong magnetic field, our LVM systems use permanent magnet lenses. These can be manufactured much smaller, which is one of the key reasons why the whole instrument can also be much smaller. Permanent magnets bring several other advantages as well. They don't produce heat, so there is no water or other kind of cooling and no additional infrastructure needed. And those of you who work with traditional TEMs, you know that at the beginning of every session, you have to go through a rather annoying 10 to 15 minutes alignment procedure. With LVM, this is not necessary because permanent magnets are stable for hundreds of years. So our permanent magnet electron optics stay stable for a very long time. The system is aligned at the factory, checked again after installation at our facility, at your facility, and that's it, no daily alignment. And because of this whole concept, LVM microscopes also have very low power consumption. All you need is one standard electrical socket, no extra facilities, no special power requirements, and nothing like that. The compact column also offers several other advantages beyond enabling the device to be built in a compact or benchtop form. It's also contribute to mechanical stability. A shorter column with a dimensions ratio closer to a cube is less sensitive to vibration compared to longer rod-like columns, which are less solid. This entire configuration is further optimized by upside-down design, which situates the cathode at the bottom to ensure lower center of gravity. Another interesting technical aspect of our LVM systems is so-called two-stage optical concept. This idea has been around since the early days of transmission electron microscopy. The electron image is first formed on a fluorescent screen, then converts the electron image into the light image, and that light image is then further magnified by a small optical microscope. However, in conventional high-voltage TEM systems, this additional optical magnification is very limited. High-energy electron excite a large volume inside the fluorescent screen, which means each pixel on the screen is quite big. If you try to magnify it optically too much, you very quickly reach empty magnification. You are not seeing more details, just a bigger blurry image. In low voltage TEM, the situation is completely different. The excited volume in the screen is much smaller because of low energy of electrons. This means each pixel of the image on the screen is much smaller also. So we can magnify it optically much more before reaching this empty magnification. And to make the system even more versatile, we include a carousel with exchangeable optical objectives, so users can easily switch between different levels of magnification depending on their application. Now, once we've covered the key principles and the unique technical aspects of low voltage TEMs, it's time to move to the part that most of you are probably looking forward to, the applications, some very nice images. In this second part of the presentation, I would like to show you what the LVMs can actually do in the real research scenarios. Today, the main star is going to be the bigger system, the LVM25E. So let's a little bit dive into some real examples and see how the LVM25 performs on everything from delicate biological samples to some advanced materials. If I would try to find a single word to describe this whole instrument, I would probably choose word versatility, because as you will see, the possibilities of this device are enormous. This electron microscope is referred to as an all-in-one microscope. It's not just because the column and all electronics are placed in one single case, but also because it can be equipped with all main microscopic modes. LVM25 is not just TEM, but it can offer much more. Every single optional mode significantly expands the application range. Thus, the application area of the microscope are extremely wide, and it's very powerful and versatile. The most typical sample for the LVM25, and in fact, the type of the sample this instrument was originally designed for, are biological sections. It's an ideal tool for hospitals and routine diagnostics because it's very easy to operate and provides exactly the information needed for an accurate diagnosis with minimal effort. Right from the first glance, you can see the exceptional image contrast we talked about earlier. In medicine, the main application areas are the diagnostic of kidney disease and neurological disorders, where contrast is essential for identifying structural changes. Many of our customers initially bought the LVM25E simply as a routine instrument to complement their big TEMs and help reduce their workload and queue. However, quite often they very quickly realized that there is no better tool for imaging biological sections than the LVM25. It's not just a conventional routine system, it's a powerful research instrument capable of delivering valuable data even for advanced scientific studies. One of the most important application area for the LVM25 through its entire history has been virology. For laboratories that study and identify viruses, it has always been a highly valuable instrument, not only because of its imaging performance, but also because it can be installed directly inside biological contained rooms to secure sealed spaces where infectious viruses are handled and from which pathogens cannot escape. And in these facilities, people especially appreciated the small footprint of the instrument because LVM25 could fit into rooms where conventional TEMs would never simply fit. The LVM25 offers exactly the resolution needed to visualize and identify the structural details of individual variants. So it's a really good device for virology. It produces excellent results with negatively stained samples And again, it can even help reduce the amount of staining agent required for these analyses. But just to be clear, we are able definitely to work also with stained samples. There are many other areas where you can benefit from the low voltage technology. For example, in pharmacology, we see a wide variety of interesting samples, and pharmaceutical companies especially appreciate that the LVM systems are affordable, require no construction modification, and are really easy to use for large groups of users without the need for a specialized core facility. For pharma labs, the LVM25E and also LVM5 is an excellent tool for imaging proteins and various lipid-based particles that are used as a drug delivery system, such as, I don't know, exosomes, liposomes, and similar nanoscale carriers. These structures often consist of light elements, and can be beam sensitive, which makes them the ideal candidate for a low voltage approach. As I already mentioned, when you want to investigate particle-like samples, the TEM mode is the right choice. And the LVM25 is not limited to life science application at all. It's also an excellent tool for characterization of a wide range of nanoparticles and nanomaterials across the entire spectra, from simple inorganic particles to more complex functional nanostructures. There is also SEM mode in the dedicated TEM. SEM mode is especially useful for samples that are partly transparent and partly bulky, because it allows you to analyze all parts of the specimen in complementary way. It can be also very effective for immunolabeling, for example, where metallic particles really stand out thanks to the strong material contrast provided by the backscatter electron detection. And even if SEM imaging is not your main focus and it's not the main mode of the microscope, it's simply convenient to have a SEM capability available in the same instrument, ready to use whenever an SEM type sample appears. Now, with a new version, LVM25E, we can already perform also dark field imaging in both TEM and STEM modes. And in STEM, we can also acquire high angular annular dark field information. These modes can be especially valuable for material scientists, of course. Regarding the operation, the transition into and out of dark field mode is very simple and quick. So you can switch imaging regimes easily whenever you need a different type of contrast just by clicking on the button. With version E, we are now also opening the door to metallographic applications, which were until now domain of basically only high voltage systems. Here in the image, you can see a multiple analysis of a beta phase particle in aluminum manganese silicon alloy. This single sample was examined using through all modes, TEM, SEM, STM, electron diffraction, and also dark field scanning transmission, all within one instrument in one session, simply by just switching imaging modes. This example nicely shows how low voltage imaging and diffraction, electron diffraction, can complement each other, giving us both high contrast morphology and detailed structural information from the same region of interest. Together, all these modes let you piece together the puzzle of your sample, and each one adding a piece of information until the hidden story of the specimen is fully revealed. So to wrap up everything, here are the key points I'd like you to take away from this presentation. Our LVM systems operates in the 5 to 25 kiloelectron volts, and this low voltage approach gives them several clear advantages. The most important one is the enhanced image contrast. especially imported for samples made of light elements, something that is often challenging for conventional TEMs. You've also seen the unique concept of our electron optics based on permanent magnets, which enables the compact design, excellent stability, and very low infrastructure requirements. And of course, two-stage optical systems, both the LVM5 and the LVM25 are kind of versatile instruments that combine compact size with a wide range of imaging and analytical modes. TM, STEM, scanning transmission, SEM, electron diffraction, and elemental analysis with EDS within a single platform. And when it comes to applications, LVM can handle everything from 0D quantum dots all the way to 3D bulk materials in SEM across both life science and material research. So that's everything from my side. Thank you very much for your attention, and I'm ready for a question if there are any.